So let's start off with reviewing the integrals that we should already know. So I'm going to encourage you at this spot to pause and try to write down all those integrals from working backwards from the derivatives. All right, let's see how you did. So the integral of sine, okay, that's whose derivative is sine, that's cosine, so that's going to be a negative. That doesn't have a negative, so it needs the negative. So the derivative of negative cosine would produce a positive sine. Derivative, whose derivative is cosine? That's sine, so the integral of cosine is sine. That's pretty straightforward. No negatives to worry about. Whose derivative is secant squared? That's tangent. Hopefully you remembered your plus c's. Whose derivative is cosecant? That's a co, so it's going to need a negative. That's cotangent. Secant tangent, it always starts with the 1. Secant starts with secant is what I mean. And then the same thing, we've got a co here. So this is negative cosecant of x plus c. If you do not have these memorized, not just the AP test takers, but everybody needs to know their trig derivatives and integrals back and forth. Okay, so we've got these bad boys. Well, what happens when we try to just integrate? We did the integral of sine, we did the integral of cosine, and then we could do these special integrals that we already knew were the derivatives of something else. What happens when we want to just integrate tangent, cotangent, secant, cosecant? Well, we're going to think about these in terms of similar to how we did our u-du substitutions. So I'm going to think about another way I could rewrite tangent. Well, you probably already guessed it. We could rewrite tangent as the integral of sine over cosine. Now I can't integrate a division problem, but I can do my u-du substitution. So try to think about which one would make sense to make it into u. So let's have you try to think, who would you make u? Okay, hopefully you came up with cosine should be a good u because that's the thing on the bottom. So another way that you might want to think about some of these problems is to rewrite them. So this is the sine of x times the cosine of x to the negative 1 dx. Now it becomes a little bit more obvious who's inside. So my inside function is cosine. That means du would be the derivative of cosine is negative sine of x dx. So if I wanted to do a rewrite, I'll do this one the long way. So I'm going to need, I don't have any constants. I need to account for a negative, so my correction would be a negative 1 out front. Then the integral of, okay, so the negative that I'm making and the sine x and the dx are all going to roll together to make du. And then cosine of x is u, so that's u to the negative 1. So we try to integrate this. Well, you add 1 and divide by the new exponent. So when I add 1, I get 0. When you divide by 0, you got a problem. So hopefully you remember, okay, so how do we integrate? Basically, 1 over u du. If you don't have this memorized yet, you better put it on the old study list. Make a list of these things that you need to know by heart. But the integral of 1 over u is natural log. So I'm going to go ahead and jump right to the answer. The integral, no I won't. Integral of natural log of not u, but absolute u plus c. And then we got to go back up here and look. Yep, right there we called cosine u. So negative natural log of absolute cosine of x plus c. My AP test takers, you need to just memorize. You don't want to have to do this every single time. You need to memorize this. My non-AP test takers, this would be something that I'd give you on a test. You don't have to memorize it, in my opinion. That might change. I'm making this video in the year 2020. So if I'm still teaching in the year 2030, maybe I'll be meaner and make you memorize them. Let's see if you can do part B on your own. So I'm going to encourage you to pause and try to follow along, see if you can come up with a move. All right, let's see how you did. So hopefully you rewrote this as cosine of x over sine of x dx, and then you rewrote it again as cosine of x times the sine of x to the negative 1 dx. Makes it a little easier to figure out who is u and du. So u is sine of x. Du then would be, the derivative of sine is just straight up cosine. So I'm not going to need a correction factor. So I'm going to try to do this one by pattern recognition. So any constants? No. Any corrections? I need a cosine x and a dx. I got a cosine x and a dx. No corrections. So my function u is something to the negative 1, which we already looked at, was natural log of absolute that something plus c. All right, so this is more for my AP test takers, and maybe, I don't know if Corpy got a little sneaky on his homework, but I want to talk about another way to rewrite these. So, so this negative with a natural log, remember our log properties, we can take a negative and we can bump it up to the exponent. So we could actually rewrite this as the natural log of the absolute of cosine of x to the negative 1 plus c. Well, now this isn't cosine inverse, folks. Be clear. This is cosine reciprocal. So you wouldn't be allowed to just write it in there without changing the function. So this is one of the few times that we have to be picky about how we write our exponent around a trig function. But anyway, this is the reciprocal of cosine. Well, what's the reciprocal of cosine? Secant. So you might see on a multiple choice that they might give the answer this way, they might give the answer this way. I know it's annoying, but welcome to AP Calculus. So the same idea here, I'm going to work, though I don't have a negative, so I'm going to generate a negative. So natural log of absolute. So I want to go right to the negative 1. So who's the reciprocal of sine? Notice how I'm writing this. I'm putting the negative 1 around the whole cosecant. And then now I can take that negative 1 and bump it out in front. Those are the same thing. Those are both legit answers. All right, secant's a little tougher. I tried to do secant. The first time I tried this, my plan was to turn everything, to just do the same move here. So in other words, I was going to take secant and rewrite it as 1 over cosine of x dx. And then I started to do my u du. When I did my u du, u would be cosine of x, and du would be negative sine of x dx. And that's a problem because we don't have that negative sine of x anywhere floating around. So we had to come up with a different move. Now, this is one of those that, I mean, somebody would have to show you this. There's no, I mean, somebody figured it out, but it's well beyond what I would expect out of anybody in our class, or even for myself. Don't get me wrong. I'm not trying to talk anybody down here. All right, so the way that you want to attack this is you want to look at this as, you want to start off with your secant. You got to find something to multiply by, and why this works, or how this works, is just, to me, mathemagic. It's amazing that somebody could have come up with this on their own. So I'm going to take the integral of secant of x. Now I can multiply. I'm going to put my dx in there right now. Oops. I can multiply by whatever I want. You know, I can do things like +1, -1. If I'm trying to make this thing look like something that's easier to integrate. So I can multiply by something over itself, you know, x over x or a over a or 3 over 3 or something like that. Or I can add to and subtract to, anything that undoes it. So the trick is we're going to multiply this by, oops, I just used that color. Let's go with a nice brown here. Secant of x plus tangent of x over secant of x plus tangent of x. So first of all, what am I really multiplying by? What's this worth? 1, which means it doesn't change the value of anything. But watch what happens when I distribute this. So I would get the integral of, so secant times, so this is over 1, right? Secant times secant is secant squared x plus secant x tangent x over secant x plus tangent x. And then don't forget your dx here. Okay, so now I'm going to go back and I'm going to start to du this thing. So which piece is inside? Well, this looks like the nastier piece, but it's not inside of anything. It's on top, right? If I were to rewrite this, this chunk here would get bumped up to the top with a -1 attached to it. I'm going to choose that to be my u. Secant of x plus tangent of x. Ready for some mathemagic? Du, my derivative, what's the derivative of secant? Is secant tangent. What's the derivative of tangent? Is secant squared. Which amazingly, whoever, like I said, it's pretty amazing whoever came up, I don't want to get rid of that so I don't confuse myself. Pretty amazing whoever came up with this. So this here, all of this is going to roll together to become my du. And I'm going to have 1 over secant. So this really becomes the integral of 1 over u du. Who'd have thunk it, right? So we know how to integrate 1 over u. The integral of 1 over u is natural log of absolute of u. U for us was secant of x plus tangent of x. And then don't forget your plus c. Try D. I know it's going to be pretty tough, but try to build off of this idea and see if you can figure out how D is going to work. Okay, let's see how you did. So I'm going to start off by doing this kind of multiplying situation again. So I'm going to have, right now I have the integral of cosecant of x. I don't know why I didn't just write it here, but oh well. What could I multiply by in a similar idea to what I did up there? I'm going to multiply by, instead of secant x plus tangent x, I'm going to multiply by cosecant x plus cotangent x over cosecant x plus cotangent x. Distribute again. So I now would have the integral. Cosecant times cosecant is cosecant squared. Cosecant times cotangent is cosecant cotangent over cosecant x plus cotangent x dx. Pick your u's and d's again. My u would be the thing on the bottom. Cosecant x plus cotangent x. Du, derivative of cosecant, is negative cosecant x cotangent x. Oh boy, can I make it in there. Minus derivative of cotangent x is cosecant squared of x. Okay, so let's look back at what we have and what we need. So I do have a factor that I need. So this stuff's going to roll to make my du, but I need a negative. The integral of, so all of this with the negative and the dx, I'm sorry, becomes our du, and I still have 1 over u. This time I decided to write it as u to the -1. To remind myself, add 1 to the exponent, I get 0. Try to divide by 0, I have a problem. So that's my reminder that I'm going to have a natural log absolute of my u, which is cosecant x plus cotangent of x, plus c. Whew! My AP test takers, start memorizing. I don't know what to tell you, man. I don't know what to tell you. There's no way to shortcut it. I wish there was some simple way that I could say, oh, good luck. It's a lot, but it's doable. Hey, man, people get 5s all the time. Not all the time, but they get it. So you're not going to get there. You're not going to be among the best if you're not willing to do what they do. Okay, so let's see if we can handle some of these. Let's have you try these. I think you could try both of them. If you want to turn it on in a second to see how you did with the first one, that's fine. But pause it, give it a whirl. All right, let's see how you did. So I'm going to start off, I'm going to integrate tangent, but I've got something inside, so I can't go directly. I'm going to have to do a u-du. Now, right now, it feels like we do u-du every single time. But try to always still look and see if you don't have to do u-du. So if you can do this without, so in other words, this is u-du is kind of like the anti-chain rule. If you need to do the chain rule to derive something, you usually need to do a u-du to anti-derive it. All right, so I'm going to try to do this one with pattern recognition. Do I have any constants? Yes. What do I need? I need a 3, an x squared, and a dx. I've got the x squared. I've got the 5 taken care of. I've got an x squared. I need a dx. So I need to create a 3, which means I need a correction of 1/3. My u is this stuff in here. So what's the integral of tangent of u? I already forgot. Tangent of u is, it could be either one. I don't care which one you want to use. I don't care. I'm going to use negative natural log of absolute cosine of the quantity x cubed plus 1. Don't forget your plus c. So now I clean this up a little bit. Negative 5/3 natural log of absolute cosine of x cubed plus 1 plus c. And keep in mind there's the secant version of it too. I don't know. On a multiple choice, they might bounce back and forth, so you have to know both of them. So let's see how you did on that one. Let's pause again and try this one. Alrighty. So can I just integrate it? No, because I've got too much stuff. If I asked you to derive this, there would need to be a chain rule. So to do this messy part, I'd need some chain here. So this is going to be a u-du. My u is the inside function. That's e to the negative x. Du would be the derivative of that. So the derivative of e to the something is e to the something times the derivative of that. So I actually could do that part in my head. I knew there'd be a negative in the mix. All right, any constants? Yes, I got a constant of 2. Any corrections? I need a e to the negative 1, check. I've got a d to the x, check. I need a negative 1, so I already took care of that. So I need a negative. I'm just going to put the correction with the 2 since that's a simple correction. This is u. So what's the integral of secant of u? Natural log of a lot. Natural log of absolute value. Secant of. Now, the first time I did this, I wrote x here. Be careful. It's the secant of, it's secant of x here. Secant of x here because I'm doing secant of just x here. If this changes to a new function, that has to be that new function as well. So in other words, if this is u, those have to be u's. So what I'm saying here is I need to now put back in secant of u e to the negative x plus tangent of u e to the negative x. So the first time I did that, I fell for it. Don't fall for the same trick. I'm not going to rewrite all that again just to get rid of that multiplication symbol. So we'll call that good. All right, so next up, we're talking about throwing all this stuff into the same pile and making sure that we notice when we need to do our tricks from the front and when we don't need to do those tricks. So, and you know what I mean? I meant like tricks from the front, like when do I need to UDU it, and when can I do one of my trig rules or something along those derivatives. So let's look at this one, and I recommend trying to rewrite it first. So do a nice little rewrite so that it's easier to see who is inside of who. Or whom. Probably one of those. I don't know which one. The integral of. All right, so the x is x. This thing was on the bottom, so I'm going to bump it to the top. X squared minus 4 to the negative 1 dx. Check to see if you can just integrate that first. Well, no. Two reasons. I've got the product rule kind of situation, and I've got chain. So now I'm going to try to do a UDU. So my inside function would be x squared minus 4. My outside function would be 2x dx. Do I have what I... Yes, life is good here. I have what I need. So I'm going to just do a pattern recognition here. I don't have any constants. I need a 2, so I don't have that. I need to create the 2, which means I need a correction of 1/2. I've got an x, I've got a dx, I've got u to the negative 1. The integral of u to the negative 1 is natural log of absolute u, x squared minus 4 plus c. This one's sneaky because it's kind of tough to try to decide who is who. Who do you want u to be? So it depends on how you're looking at this. So if I were to rewrite this, well, let's go for it. Let's see what happens. So let's just choose to, we'll rewrite it. We'll do a rewrite. So for me to rewrite this is the same as 5 times, that's a constant. What is this? This x on the bottom is the same as 1 over x times the natural log of x that was on the bottom. So that's to the negative 1. Now let's say for a minute, let's just say that you choose this time you want this to be u. I just want to show you that it's not. Sometimes it doesn't work out. Remember, this is x to the negative 1. So what's the derivative of x to the negative 1? Yep, negative 1 x to the negative 2 dx. Well, we don't have that. We don't have an x squared on the bottom, basically. So we know that this guy's got to be wrong. So what's our other option for u? Is natural log of x. So then du, well, what's the derivative of natural log of x? 1 over x dx. And that makes me happy because I have a 1 over x dx. So it doesn't look like it, but that x on the bottom, remember, is really a 1 over x. Okay, so I'm going to do... I'll do a pattern, and let's write it out. I'll do a UDU. I'll do a full UDU. So I take out the constant. What do I have? What's going to make my du? I've got a 1 over x, so my 5 is out front. My 1 over x and my dx come together to make my du. Natural log is u, but where's that u then on the bottom? So that becomes u to the negative 1. So let's integrate this. So this would be 5. What's the integral of u to the negative 1? I add 1, I get 0. I try to divide by 0, I got a problem. So that's natural log of absolute u. What did we call u? Another natural log. Now, I don't need another absolute value here because this one didn't have an absolute value around it. But I do need a plus c. All right, let's have you try to do a rewrite. Maybe there might be enough room to squeeze it up on top of it. So see if you can rewrite this thing to help you decide who should be u and who should be du. So I rewrote this as the integral of, so I'm going to take that 1/4 out. That's a constant, right? That constant 4, but that 4 is on the bottom, so I got to take it out as on the bottom. Then I also have a 1 over x, and I also have a natural log of x that's getting raised to what power? I got a cube root around a squared, so that's to the power of 2/3 dx. So who would be a smart choice? I would go with natural log again. Natural log's derivative is 1 over x dx. Life is good there. So if I were doing a u du on this, I have my constant out front. Do I need any corrections? No. The 1 over x and the dx are going to come together to make my du. My u is natural log of x, so that's u to the 2/3. And now I have something that's pretty easy to integrate. So I got my 1/4. U to the add 1 would be 5/3. Then I need to divide by 5/3, which is the same as multiplying by the reciprocal. And then don't forget to actually go back and put your the u value back in there. So I've got 3/20 times the natural log of x to the power of 5/3 plus c. All right, you're on your own. Well, for a couple minutes at least. Try to do part E. Pause it, give it a whirl. So I'm in the same situation where I want to try to rewrite as much as I can. Any constants? Yeah, this is an E. That's not a variable. That's that Euler's number. So I can pull that constant out front. 1 over E times the integral of cosecant. Dang it! I almost wrote cosine. Cosecant of natural log of x dx. It's pretty obvious who's my inside. U is natural log of x. So du is 1 over x dx. Uh-oh, do I have those things? Oh, I didn't account for that. Oops, I wasn't paying very good attention. I've got my cosecant of natural log of x. I've got my e on the bottom pulled out front, but I never accounted for the over x. So I'm going to just write it down there. A constant, yep. Correction, nope, because here's, 1 over x dx. Cosecant of, we said that natural log was u du. So 1 over e times integral of cosecant. Thank God I don't have to take the test, the AP test. Those who do, you're going to want to memorize. So it's negative with cosecant and cotangent. So negative natural log of cosecant. What, just x, right? No. U plus cotangent of u plus c. Now that's not an acceptable answer because they don't give a crap what your function is with u in it, and they want the x's back. So I would have negative natural log of absolute cosecant of natural log of x plus cotangent natural log of x all over e and then plus c. Okay, so this is another one that I'm still struggling to memorize. Hopefully, in the years that I've taught since I've done this video, I'll have these memorized eventually. So I want to look at first the derivatives of one of these because I can pick, so let's say I pick u to be 1 plus x squared. Well, then du would be 2x dx. And that's not going to help me at all because I don't have any of that on the top. So let's take a look at arctangent. What's the derivative? D dx I'll cross that one out so we don't get confused. Cross that out. That did not work. Well, what if we take u to be arctangent? I like to write it with the negative. We'll write arctangent. I usually like to write it with the -1, but whatever. Du would be, my AP test takers, what would it be? Hopefully you've got it memorized. For the rest of us, 4.1 notes, 4.1 notes. These are the antiderivatives, so I want to work the other way. Arctangent, so that's 1 over 1 plus. Oh, that's a good sign, man. That's a good sign because that looks a lot like what we had. So I can now go back here and say the derivative of arctangent is 1 over 1 plus x squared dx, which I have up here in my equation. So if I separate arctangent, I've got 1 over 1 plus x squared dx. So then I can now rewrite, I don't have any constants, I don't have any corrections. This is just strictly the integral of u, du, which would become u squared over 2 plus c, and then we would put c back in there. Arctangent of x squared over 2 plus c. And if you wanted to, you could put that squared there, or you could leave it like this. So let's do a definite integral. Evaluate the following two ways using pattern recognition and u-substitution. I'm not going to do it both ways. You pick which way you want to do it. I'm going to do it with u-substitution. So pause, give it a try. Let's see how you did. So u-substitution, you could do Pascal. You want to do Pascal, and then you don't have to do any sort of substitution. Do a little Pascal. What's that? 1331. Clean that up, then distribute the x, and then integrate by the sum difference rule. No problem. I'm going to use u's and d's, u du though. So my inside function is x squared plus 1. So du would be equal to 2x dx. So if I did a rewrite, I don't have any constants. I do have a correction. So I want it to be 2x dx. I have the x and the dx, so I need a 2, which means I have to correct a 1/2. The integral of, I said u was x squared plus 1, so that would become u cubed du. This is something that I can integrate. So this would be the integral of 1/2. My bad. The integral would be 1/2 times u to the 4th. Oh, 0 to 1. Sorry, we have a definite integral this time. So 1/2 u to the 4th over 4. Now remember, when it's a definite integral, we go like this, and then we write what those boundaries are in here. Be careful. I'll do it in a different color. Be careful here. Right now, 0 and 1 are the bounds for the... I actually shouldn't even have written them here. I shouldn't have written them here at all. You need to convert your boundaries. I messed up there, sorry. You need to convert your boundaries into what's happening for your new function. So what I mean by that is my lower limit was 0 for this function. Well, that's when we were talking about x's. So my lower limit now is going to become 1. Scribble this out and write a 1 there. And my upper limit is going to become a 2. Take 1 squared is 1 plus 2. You have to convert your boundaries if you're going to convert your units. Now, if we could do this, let's say we did this. Oh, we'll go ahead and finish this. So be careful. My limits go from 1 until 2. which would give me, now I don't have to plug back in this junk anymore. I don't have to finish this because I converted my boundaries. So now I can just plug these in for u. So this would be what? 2 to the 4th over 8 minus, put 1 in there, 1 to the 4th over 8. That's 16. Take away 16 eighths, take away 1/8, which would be 15 eighths. So if you're going to integrate with u's, you need to make sure that you convert your limits, your boundaries, your definite boundaries to u's. Now let's say that you did this by pattern recognition. Pattern recognition, you wouldn't have to worry about that. So here's our stage. Let's do some pattern recognition. Do we have any constants? No. Do we need any corrections? Yes. 1/2 times, what's the integral of, this would then become u cubed. So then this would become something cubed, x squared plus 1 to the 4th over 4. Now, my variable is still x, which means I'm going to use the original boundaries from 0 to 1. If you're going to plug in, you've got to make sure that you're plugging it into the right spot. You're plugging it in for x, or you're going to be plugging it in for u. When I evaluate this, you're going to see that we're going to get the same thing. So now I'm going to put 1 into this mess. Well, what's 1 squared plus 1? 2. So I would get 2 to the 4th over 8 minus, now I'm going to put 0 in there. That's 1 to the 4th over 8, which still gives me 15 over 8. So you have to be a little bit technical here on your write-ups. If you want to do this without showing u/du substitution, then make sure that you convert your boundaries. Now, if you're going to change this back into x stuff, then you have to change this back too. But you can't leave this as 0 and 1 if you're talking about u's. So I'd like to get through this next, maybe the next 2 pages, if we can. So this is a quick review of, well, maybe I'll stop then. I'll do this one, the next one, because this kind of seems like it fits together.